All right. Wow, this is a huge group right now. So thank you all for being here. I'm Brian Campbell, and I am a NASA Senior Earth Science Specialist in the United States. I work at the NASA Wallops Flight Facility in Virginia, the state of Virginia. And I am the lead for the Trees Around the Globe Student Research Campaign. And we are in our 6th year of the campaign. And this is the 69th webinar that we've had for the campaign. And today we have some special features for you and speakers from JAXA. And we will be doing some things we normally do during our, during our webinars. We're going to talk a little bit about the campaign, but I'm going to give you a quick, brief rundown of what the campaign actually is. The Trees Around the Globe Student Research Campaign, as I mentioned, is in the 6th year, and it's primarily for students and teachers around the world through the GLOBE program, which is funded by NASA and is active in 127 countries, including Japan. And our campaign, we have active participants from 63 of those countries. So we're super excited about that. And Japan has a pretty big role in the GLOBE program. You've been, students and teachers in Japan have been part of the GLOBE program for many years now. I'm pretty sure about 15, 20 years. So that's wonderful. So today we're having one of our campaign webinars. And since I'm here in Chiba, we wanted to do it live here. And thank you all for being here. This is great. So today we're going to talk about the state of trees, May 2024. And of course, we're live here in Makuhari Messe, and this is the Japan Geoscience Union Meeting. And we will be, as I mentioned, focusing on some really amazing JAXA products and presentations today. And then following the presentations, I will pass it over to my colleague, Peder Nelson. He is online. I'll let him introduce himself in a second, but he is at the Oregon State University in Oregon in the United States. And you'll hear from him. He's going to talk a lot about NASA data sets and other data sets that correlate to our campaign and what we're talking about today. So Peder, do you want to quickly introduce yourself?
Thanks, everyone. Brian did a great job of introducing me, and I am really excited to join you and share with you some of the wonderful ways that you can get involved in our space science.
All right, awesome. Thank you, Peder. Do the next one. All right, so with our campaign webinars, we usually have a kind of an inspirational quote from someone famous around the world. This happens to be Henry Ford, okay? Anybody ever heard of Ford cars? Yeah, pretty common, around, well, not as common here as they are in the United States where they were born, but I like to find some really cool inspirational quotes because the purpose of this campaign is to have students from around the world take observations and share it with the rest of the world. Like I said, the GLOBE program is 127 countries coming together in the name of science and observation and looking at how our planet is changing over time. Something that NASA, that's one of the primary goals of NASA and NASA's Earth observing missions, to look at the planet and see how they're changing over time through measurements and observations. So coming together is a beginning, staying together is progress, and working together is success. I just like that quote because we literally have students working on research projects from different countries around the world every year. And we have something called the International Virtual Science Symposium that students submit research projects that get judged like a virtual science fair. And this year we had a record. We had pretty close to 300 student submissions to this symposium. It's basically a big, giant virtual science fair. The topics range everywhere from land cover to tree height to air temperature to mosquitoes and to eclipse to clouds to anything you can imagine that you can measure in the environment. There's usually a presentation that students have designed around it. Next, Steve. So here's a webinar. The agenda, there's a lot going on here, okay? But our two speakers, Dr. Masato Ohki, a senior researcher at JAXA Earth Observation Research Center, We'll be talking disaster monitoring by Advanced Land Observation Satellite ALOS-2, also called IG-2, satellite methods and social implementation. Then we have Mr. Kosuke Yamamoto, also a researcher at JAXA Earth Observation Research Center, EORC. He'll be talking about precipitation seen from space, the GPM mission, which is the Global Precipitation Measurement Mission. It's a joint mission between NASA and JAXA. And he will be talking about that and the hydrology, because with this campaign, we really focus on tree height, land cover, carbon cycle, and what's called greenings, green up and green down. Green up and green down is pretty simple concept. In the springtime, when all the flowers start blooming and you get buds on the trees, that's green up. And then in the fall and winter, when the leaves fall off trees, the trees die out and the photosynthesis slows down, that's when we have green down. So all of these measurements are part of our campaign. And with the campaign, we focus on taking observations as well as making sense of the observations, because anybody can take measurements. Okay, you have to be able to make sense of the measurements. And then we also want people to be able to figure out how to use NASA satellite data in order to compare or align to the data that they've taken in their local environment. And then after that, after the two presentations, after each presentation, we will have a question and answer where you'll get a chance to ask the scientists some questions. We'll take about up to 5 questions per scientist because of our time limit here, because we have a lot of things going on after this webinar today. Here we have lots of speakers who are going to be presenting here on the Hyperwall from JAXA and NASA. I'm doing a presentation later on today. But then after that, we will go back to Peder Nelson and we will talk about he will talk about some of the really cool data sets. And Peder is a data scientist. He's also a professor of cartography. So he works with the data all the time and creates really good models of how to use the data and how to visualize it as well. And then at the end, we will have any final question and answer session. Does that sound good? There's a lot going on. I know it's a little warm in here because I can see lots of people fanning themselves. Sorry about that. When they have a lot of bodies in a small area like this, it's bound to get hot. I'm not comfortable in my jacket. It's very hot in here, but I'm going to wear it anyway. So next, Steve. All right. So once again, there's a lot going on here, but I show this before every webinar. Okay. These are the years of our campaign, year 1, 2, 3, 4, 5, and then we're in year 6. And as I mentioned, we focus on these measurements. So you can see here, every year, we've gotten more measurements associated with the main observations related to the campaign: tree height, land cover, and green up, green down. And right now, we are in year 6. This is year 6. It started October 1 of 2023. And since then, we have, you can see all the numbers. We have almost 12,000 tree height measurements from over 3,400. And total right now, this is as of yesterday afternoon, we have 27,201 measurements from almost 7,000 global locations since October 1st of 2023. Next. And this is what's called the globe visualization system. It's an image that I took where all the measurements that have come in for the campaign since it started on 15 September 2018. We're almost at 100,000 tree height measurements for this time, but we have all these measurements, we're almost at 200,000 students from citizen scientists around the world using the GLOBE program. So, and like I said, this is the 69th webinar. We've actually had a bunch of special webinars as well related to the campaign where we've talked to specific regions of the world. And then also I mentioned we have participants from 63 countries. Next. All right, so I'm sure all of you have heard of JAXA, right? Okay, of course, right? JAXA, the Japan Aerospace Exploration Agency. Next. So here is a map showing where all the JAXA opposites and facilities are in Japan. Okay, did you think there were that many related to JAXA? There's a lot, right? Kind of like NASA, we have basically 10 centers across the United States. okay, with our headquarters being located in Washington, D.C., in our country's capital. But here, I just want to give you an idea of, where all the offices and facilities are for JAXA. So the next one is going to be next slide is going to be a video. So hopefully the sound comes out okay online as well. But it's a short video about kind of it's the history of JAXA. Yeah. So you can see with that short video, there was a lot in that video, and JAXA has been involved in global space exploration for over 6 decades, 60 plus years. So that's why at NASA we love partnering with JAXA, because the JAXA scientists are top notch. The great scientists doing amazing things, and that's why we partner with JAXA as much as we can. And that's why we have some speakers from JAXA, the Earth Observation Research Center, here today for the webinar. Next. All right, so our 2 speakers today, as I mentioned briefly, we will start off with Dr. Masato Ohki, a senior researcher at Earth Observation Research Center, EORC, at JAXA. And once again, he will start off by talking about the disaster monitoring by Advanced Land Observing Satellite 2, ALOS 2, also called JpGU satellite methods and social implementation. And then we will have questions and answers for that. Like I said, we'll start off in the crowd here with all of you. If you have any questions for the speaker after the presentation, like I said, we'll do about 5 questions from the group here. And then we will pop online to see if there's any questions in the chat, or anybody who's online can mute. I saw that we have folks online from different countries right now, from the United States, from Switzerland, and some other countries as well. So, and they see some of you. We have one of the, that camera is turned, but it'll be turned back to you at some point. And then after the question and answer with Dr. Ohki, we have Mr. Kosuke Yamamoto, and he is from the same location at JAXA, the EORC, and he'll be talking precipitation seen from space with the GPM mission, overview and application in hydrology. All right, so what I'm going to do now, I'm going to pass it over to Dr. Masato Ohki. He is going to be doing the presentation virtually. He is away from Chiba right now, so he's going to be presenting virtually. So I have to go ahead and unshare my screen so he can share his and start his presentation.
Okay, so yeah, Masato Ohki speaking, and please turn off your screen sharing so that I can share my screen. Okay. Okay, can I start the presentation? I cannot hear you, but I hope it's okay. Brian, can you hear me?
Can you hear me, Masato?
Yes, your voice is clear now.
Okay, go ahead. You're all ready to go. Thank you.
Okay, thank you very much. So, yeah, hello everyone. And yeah, sorry, I couldn't be there with you in person because we are having busy days for preparing for the launch of a new satellite. So today, I'm going to talk about disaster monitoring using ALOS 2 and 4 satellites. ALOS 2 is an ongoing mission. It is already launched, and that it has been working in space for more than 10 years. Actually, last week we celebrated the 10th anniversary of this successful mission. And ALOS 4 is the next generation satellite, which will be hopefully launched soon. So, yes, and I forgot to introduce myself. I am Masato Ohki from Earth Observation Research Center, JAXA, and I have been working on Earth observation research works for more than 10 years. And today I'd like to introduce our activity on disaster monitoring using satellites and its application and its social implementation for social benefit. So first, please look at this image. This image shows the area around Kaihin-Makhari Station, and you can clearly see the baseball stadium. And now you are around here. Sorry, this time I'm not here. Anyway, and also please look at the timestamp of this image. This image was actually captured at midnight, around 11 p.m. So why can we capture such a clear image even at night? That's because this satellite uses a special instrument called synthetic aperture radar. So what is synthetic aperture radar? It is a kind of remote sensing instrument to capture satellite images. But it's quite different from normal satellite imaging. As you can see in this video, I try to repeat this video. Yes, as you can see, SAR, synthetic aperture radar, or SAR in short, the SAR transmits a beam, invisible microwave, onto the ground, and it also receives the reflected microwave from the ground and capture images using the reflected microwave. Using this technique, we don't need sunlight for imaging. Instead of observing sunlight, SAR illuminates the ground surface with invisible microwave. So we don't need sunlight to capture satellite images using this satellite. That's why we can capture a clear satellite image even at night. And also, as shown in this video, the microwaves we are using with this satellite is slightly longer wavelength microwave that can penetrate through the clouds. So we can even see the ground surface under the clouds or rain or any other weather condition. So the advantage of SAR or this satellite is all weather and day and night imaging capability. So using this capability here, let me show you the comparison of SAR image on the right side and optical image on the left side. And these two images were captured simultaneously. I mean, these two images capture the same area at the same time. In the optical image on the left side, you can see the a volcano erupting here on the top right corner, and we cannot see the ground surface under the smoke from volcano here. On the other hand, in the third image on the right side, we can see the ground surface even under the smoke, beneath the smoke. So it provides very important information about what actually happened in at the ground surface during the eruption. So this is the time series close-up images showing the lava dome growth of the volcano. Based on this information, Japan Meteorological Agency reported the evaluation and the outlook of the volcanic activity of this volcano. So I want to emphasize that SAR-derived information is already used in decision-making, such as determining alert levels or evacuation zones. And yes, going back to the talk about the satellite itself, as I mentioned, we are now operating EORC satellite, which was launched in 2014, and we celebrated 10 years anniversary last week. And I think some of you may know this, but we had also an optical satellite named EORC, but unfortunately, it was lost due to the launch failure. And we will soon launch the next satellite, EORC-4. So if time allows, I will talk a bit more about the next generation satellite at the end of this presentation. So now we are operating EORC-2, and it has 4 primary objectives: monitoring disasters such as flood, landslide, earthquake, volcanic activities, and many other types of disasters, and also monitoring environmental things such as forest, mangrove, or ice monitoring. And third, agriculture or natural resources monitoring. And as well as the land area, it can also observe over the ocean for monitoring sea ice, ocean, wind speed, or ships. And this is the specification of the satellite. It has 2 tons of mass, and mission lifetime is 5 years, but I already mentioned it's actually working for over 10 years and still working well. And it has 23, I think, meters span from end to end of both solar panels. And SAR antenna, this white big plate is antenna to transmit and receive the microwaves. And the antenna has 10-meter length in flight direction and 3-meter width in traverse direction. So yes, this is the launch of the EORC-2 back in 2014. The left photo was captured by an automatic camera just under the launch pad, and the right photo was captured by myself. I took this picture 3 kilometers away from the launch site. The weather was clear and it was beautiful launch. I will never forget this beautiful scene. Okay, anyway, compared to the previous satellite, actually we have this kinds of SAR satellite from 1990s. The ground resolution has been improved better and better. And now, using the latest satellite, EORC-2, we can see much smaller things, much smaller objects, and much finer details on the ground surface condition. So using this capability, we can observe a variety of phenomena and human activities. So today, I will mainly focus on disasters, but also if time allows, I will talk a bit also about environmental monitoring. On flood disaster, EORC-2 can monitor its damages from many different aspects. For example, here, a bridge was swept away by the flood water. The right side is before the flooding, the left is during the flooding, and a bridge here was totally swept away by the flood water. And there are many slope failure or sediment flow or landslides, and of course flooding. And also there are a lot of trees or other debris from river that totally occupy the bay area and became obstacles for ships in the port. So many different things happen simultaneously in this single flood event. And ALOS-2 SAR can capture all of them, even at the night and even in the bad weather. And this is one of the latest results, 2024 Noto earthquake. It happened in the very beginning day of this year. And within the same day, we performed the first observation by ALOS-2 and estimated the area of flooding caused by tsunami induced by the Noto earthquake. Yeah, red is the flood area here. And this is an example of volcano monitoring, volcanic monitoring. This is the Soufflé volcano in St. Vincent Island. This event happened in 2021. And this impact for animation shows that a new lava dome appeared here, and it inflated gradually, but finally a massive eruption occurred and completely blew up everything, blew up the lava dome. So ALOS-2 successfully captured the entire process of this volcanic event. This is another example. This is Hawaii eruption in 2018. In this event, a large amount of underground magma moved from the western region to eastern region. And then the magma erupted from the eastern region. And as you can see in this image, lava flow is emphasized as red color. And as you can see, the magma erupted from fissures and flowed into the ocean. It happened in eastern region, and on the other hand, in the western region lost the magma because underground magma was moved from west to east. So western region lost magma, lost the volume, underground volume. So it resulted in the collapse of the crater. So ALOS-2 can successfully capture the collapse of the crater, volcanic crater in Hawaii Island. And this image on the top right corner, this figure is the displacement map. In this map, red color, for example, indicates the 80 or 90 centimeters subsidence happening in this region. So this displacement map was also obtained from ALOS-2 data. So we can obtain not only the image like this and like this, but also the displacement map, very precise centimeter level displacement map also. So how can we measure this centimeter level displacement from ALOS-2 data? What we did here is a phase analysis of microwave by measuring the phase difference between two observations. For example, before and after the eruption, we can estimate the displacement, or more precisely, the change in the distance between satellite and ground target. The wavelength we are using here is 24 centimeters. So this is a 24 centimeter wavelength microwave. And for example, one phase cycle corresponds to 24 centimeter change in distance. So this method is called interferometric SAR analysis, or Kansho SAR kaiseki in Japanese. So again, when ground moves, the microwave propagation distance changes between two observations before and after the eruption. And the change in distance can be measured from phase difference between two observations. So we can estimate the land surface displacement from the phase difference information. This is another example of interferometric analysis for a Sakurajima volcano in Kyushu Island, the southern part of Japan. And in this case, we observed 16-centimeter uplift in this area. And this result suggests the movement of underground magma. And here I want to emphasize that this 16-centimeter uplift, this 60-centimeter displacement could not be observed by ground GPS station because we have only 3 ground stations in this volcano, and this area there's no ground station, so this displacement can only be seen from space by this satellite. So the advantage of this technique, interferometric sound analysis, is that we can obtain a displacement map as an image, a very high resolution image, not a distributed point data. This is the advantage of the SAR analysis. This is a recent example. Again, this is the 2024 Noto earthquake. I have already shown the tsunami flood estimated result, but here we estimated the displacement by the same earthquake. And in Wajima city, in the western side of the peninsula, we can see more than 4 meters uplift and 2 meter movement based on the ALOS2 data analysis. And again, the ground-based GPS network could not capture the largest displacement because there is no ground station at the point of the largest displacement. So ALOS2 first discovered large cluster deformation induced by this earthquake. Now, slightly changing the topic, the environmental monitoring is also, of course, another important role of this satellite, important mission of this satellite. This is a time series images and time series global forest map generated from ALOS2 data. And this image shows a change map in which red color indicates the deforestation area. In red area is the tree disappearance of trees. And so this map shows the deforestation that occurred from 2010 to 2015 in Borneo Island. So I'm not a specialist on the ecosystem or forest monitoring, but this information is crucial to understand the human activity destructing the natural or Earth's natural resources, and it's closely related to the climate change problem. Sea ice is also another important mission of this satellite. SAR can also provide the key information for better understanding the Earth's ice dynamics. And it is also closely related to the climate change. The left image is the original SAR image, and the second image is an enhanced image in which the sea ice is so much emphasized. And we can clearly see the sea ice distribution in Okhotsk Sea in the northern part of Japan. And Japan Coast Guard provides daily sea ice chart like this based on ALOS2 data and other data sources. Actually, not only ALOS2 data, they are using many other data sources, but ALOS2 data plays the most important role for generating this daily map. So, and this information is very crucial for ship routing and maritime safety. So SAR-derived sea ice information is very important, not only for science or understanding global climate change, but also for our social benefits. And yes, this is also the example of sea monitoring. In this event in 2017, a large iceberg, a 200-kilometer sized huge iceberg, separated from the Antarctic ice shelf and is drifted away from the Antarctic Peninsula. And ALOS2 time series images captured the entire process of this event. So I'm not specialist on the monitoring of the environment, but understanding ice dynamics in polar region is crucial for understanding global climate change, and the satellite data is playing an important role for this purpose. In the next part of my presentation, I would like to introduce our activity in social implementation of our research, and particularly on flood monitoring. Our motivation is the flood disaster affected a lot of people. It causes a lot of human casualties and economic losses in recent decades. So the SAR should play an important role for monitoring and mitigating flood disasters because it had, as I mentioned, all weather and day and night observation capability. So it can observe flooded area even in the night or in bad weather. The flooding typically happens in the bad weather, so this capability is very important for flood monitoring. So I developed a program or an algorithm of automatic flood detection using ALOS2 data. Today, I will not go into the detail of the program, but it combines ALOS2 data and real-time flood simulation data and other data and estimate the flood extent. And actually, this part is very closely related to the next presentation by Yamamoto-san, because he's one of the developers of this flood simulation system. So this algorithm combines my knowledge on soil data analysis and his expertise on the flood simulation and precipitation measurement. So, and so that we can obtain a more reliable flood extent map. This is an example of flood area automatically estimated by my algorithm. And by implementing this algorithm, we achieved almost daily flood mapping using ALOS2. And this is how we implemented my algorithm in an operational system. Again, I will not go into the detail, but first ALOS2 observe a flooded area and transmit the data to the ground system and send the data to another system. This system automatically runs my program and automatically estimate flood area and automatically send the result to the end users via email. This is fully automatic and non-stop procedure. So flood estimation result from ALOS2 are emailed only 2.5 hours after ALOS2 observation. This is the email actually sent during the emergency response. And the email contains the result of estimated flood area and number of estimated flooded buildings. It is also automatically calculated, and other image for information for the end users. Now, I think I still have time, so I would like to introduce ALOS4, the next satellite. This is the follow-on satellite of ALOS2, carrying a new SAR with enhanced capability. For example, it can cover an area up to 4 times larger, 4 times wider than ALOS-2. Actually, observation width, swath width, it depends on the resolution, but in case of high resolution mode, the observation swath width was limited to 50 kilometers in case of ALOS-2. For example, this is again Kyushu Island, the southern part of Japan, and red marks indicates the locations of active volcanoes. And with the 50 kilometers swath width of ALOS-2, we have to choose a limited number of volcanoes to monitor. But expanded 200 kilometers swath width by ALOS-4, actually, ALOS-4 can expand swath width up to 4 times larger without spoiling the resolution or image quality. So with this capability, we can monitor all the active volcanoes in Kyushu Island at once. So this capability is very important to continuously monitor the active volcanoes in Japan. And yeah, satellite mass is 3 tons. This is 1.5 times larger than the previous ALOS-2 satellite. But it will be injected into the same orbit as ALOS-2. So hopefully we can operate 2 satellites in space simultaneously, because ALOS-2 is still working well in space. This is the preparation status of ALOS-4. The satellite is past all the tests on the ground and now being prepared for launch. This is thermal vacuum test. In this black dark chamber, this facility can simulate the environment in space, almost vacuum, and the temperature is very high. And vibration and shock and acoustic tests are also very important, because during the rocket launch, the satellite exposed to large vibration or large, very loud sound. So we need to confirm the tolerance of the satellite for a hard condition in the rocket. Okay, this is the end of my presentation. It's a summary. ALOS-2 is a synthetic aperture radar satellite. It has all-weather and day and night imaging capability. And it's monitoring disaster, environment, ocean, and many other targets, and contributing to science and social benefits. ALOS-4 is upcoming next generation satellite, and it will be hopefully launched next month. So I'm looking forward to seeing new data from the new satellite. So thank you very much for your attention.
There you go. Masato-san, can you hear me?
Yes, I can hear you now.
All right. All right, thank you so much, Masato-san, for that presentation. Does anybody first, we're going to go into the crowd here where we have an amazing amount of students here. I believe it's 160, around 160 students or so, and some others as well. Does anybody have any questions for Masato-san? Yes. And hold both of these. Okay. If you have a question, I'm gonna pass both of these. This one is so you can hear me. This one is so they can hear you. Okay. So there's a lot of technology going on right now. You can stay.
So I wanted to ask you if, like, what's the frequency of the number of times you could take observations on a certain area per week? And so I wanted also to ask you, like, what would be like your goal to like, how many observations would you like to make daily so that you can give as timely decisions as possible and like make it safer for the society in general?
Okay, thank you for the question. And this is very important and good question. And on the frequency, observation repetition frequency of this satellite, it strongly depends on how you operate this satellite. Normally, EORC-2 observation is planned almost 4 observations per year in daytime and 4 another observation in nighttime. This is regular observation. But in emergency situation, such as flood disaster or volcanic eruption, the satellite can focus on a specific area. So in maximum, it can observe twice per day. So it can observe a specific area every 12 hours by sacrificing any other observation and focus on the same area. I hope this answered to your question. So frequencies depends on how you operate this satellite. Normally, it's not so frequent, but in emergency situation, it's quite higher frequency.
Thank you, Mr. Ohki. It was very helpful.
Thank you. Anyone else? Another question? I'll pass it to you.
Can I speak in Japanese?
Sure.
日本語で申し訳ないんですけども、2つぐらい質問があって、まず1つ目は、どれぐらいの速さで飛んでるのかっていうことなんですけど、教えていただけますか？
はい、じゃあまず日本語で答えます。低い軌道を回っている人工衛星は速度が決まっていて、秒速 7km ぐらいになります。これがその遠心力で衛星が宇宙に浮いていられるために必要な速度です。So the first question is asking the speed, velocity of satellite, and I answered the velocity of low Earth orbit satellite is typically 7 kilometers per second. じゃあ、次の質問がありますか？どうぞ。
なんで人工衛星って全体を太陽光パネルで覆ってないんですか？なんかその方が発電効率とかいいかなって思うんですけど。
これはすごくいい質問ですけど、まず太陽が当たる可能性がないところに太陽電池パネルを貼る必要はないですね。太陽電池も非常に効果高いものを使っていますので、必要最低限のところにだけパネルをつけるというのがいいです。それから、太陽電池を貼っていない場所の役割もすごく重要で、宇宙空間っていうのは非常に高い温度です。太陽が当たれば、当たった場所は100度ぐらいになりますし、当たってないところっていうのはどんどん熱が逃げて、マイナス200度近くになることもあります。そういう厳しい温度環境に耐えるために、その放熱する部分とかを用意しておくことも非常に重要なので、2つの意味で全部に太陽電池を貼るっていうことはしません。必要最低限のところに貼ればいいというのと、貼ってないところも重要ということですね。
つまり、どこに太陽光が当たるかっていうのは、事前から予想ができるんですか？
いい質問です。
今日で変わったりとかはしないんですか？
はい、初めから決めています。で、この第1、2号 ALOS-2 の場合は、昼の12時と夜の12時に観測を行うんですけど、そのために必要な人工衛星の形を設計すると、昼12時の上空を、人工衛星が飛んでいるときっていうのは、太陽が、上から当たるんですけど、そういう形で太陽が当たる方向っていうのは、人工衛星をどういう軌道に投入するかっていうことで、初めから決まっているので、それに応じた設計をしているということですね。
ありがとうございます。
This question is quite different to explain in English, but she asked why the satellite is not fully covered by solar panels. It looks more efficient to provide more electric power. And I answered that we don't have to put the solar panel in entire surface of the satellite, because solar sunlight the illuminated satellite, a specific side of the satellite. So we don't have to put the solar cells in entire surface of the satellite. Okay, thank you very much for the question.
Okay, thank you. We're going to take one more question because of our time for this presenter. I want to pass it to you because I saw your hand up first. So can you pass this down both to him? Thank you. Just two.
Okay. So I might be completely wrong, but like currently, I think like we use like just normal like cameras like from space in order to like talk about like weather, or like mostly use like just normal like cameras
Can you go ahead and switch
in order
over to
to
his
like make
presentation?
decisions to like
Yeah.
make like alerts or something. Are there any drawbacks to like this like what was the thing again? ALOS?
Yeah. I know
That
the
prevented from
PowerPoint
like
photos
just
is-
becoming like
Because I'm going to
the
go right into
norm.
his presentation then.
Sorry, Brian, your voice is totally covered the question. I couldn't
Okay.
hear the question well. Terribly
Sorry about that.
sorry.
One more time.
Okay, so I think like we currently use like just like normal imaging to mostly make decisions about like weather related things, I think.
Mhm.
Are there like any drawbacks to ALOS that prevent it from becoming like just the norm in making decisions on like things about weather or like anything else?
Drawback to using the SAR data, you're asking
Or drawbacks to using like the ALOS system?
ALOS system, the radar
Yeah.
system. The image from C6 aperture radar is slightly or quite different from normal optical data. For example, the radar cannot provide the information of color of the land surface. So we need some amount of knowledge to interpret the third image. So that's a difference from the normal optical satellite image. So yeah, drawback. That's important question. Yeah, but cloudless and all-time monitoring by SAR has still have a big advantage to monitor the forest or flood monitoring, because for example, tropical forest area or mostly covered by clouds in wet season, and also the flood disaster always happen in the bad weather. So yeah, there is an advantage and disadvantage in SAR observation. I hope this answered to your question.
Okay, Masato-san, thank you so much for your presentation and your answering those questions. Sorry about the little bit of feedback there. So can we say thank you one more time to Masato-san?
Thank you.
Thank you.
All right, everyone. Now we are going to pass it over to Kosuke Yamamoto, and he will be talking precipitation seen from space, the GPM mission. So we will go ahead and pass it over to him right now. You hook up, please. Stay tuned. His microphone is being hooked up right now. And you say next, and I'll put you next. Okay.
Hi, good afternoon, everyone. My name is Kosuke Yamamoto, also from the JAXA EORC, stands for Earth Observation Research Center in Japan Institute Cancer Center. Next, please. So today I'm gonna talk about the precipitation measurement from space, but before that, I quickly introduce our Earth observation satellite programs. So this is the outlook. So the inner circle, we have the legendary legacy mission of the JAXA Earth observation program. I hope some of you already know those missions. And the outer circle, we have the satellites, which is under preparation or to be launched soon. Actually, on the very top of this figure, we have three different colored satellites. Those three are going to be launched this Japanese fiscal year. So stay tuned to be launched. And especially for Earth mission, this one is going to be launched tomorrow morning. So please look at JAXA's website or JAXA's channel, or maybe ESA, the European agency website, or maybe SpaceX website. All those have going to have the broadcast or some information about this satellite launch. So please take a look at that. Next, please. So, sorry, one more part. So today's topic is precipitation or rainfall. So I'm going to talk about the satellite which observes the rainfall or precipitation, and this one, GPM. And this is a success mission of the Olympia. Maybe some of you may have already heard about those missions. Please next. So the key question of this talk is why do we need to observe rainfall from space? So please keep in mind this question. Next, please. And one of the answer can be found in this report or booklet. Do you know this report? Oh, this is really nice. This is so-called IPCC report. IPCC stands for the Intergovernmental Panel on Climate Change. And this report is published in 2020, maybe 2022, maybe. And this is to explain the physical science basis for the climate change going right now. And in this report, we can find one very important number. Please next. This 1.1 degrees Celsius. So what is this? What is this? Next, please. Yes. This is the number that shows how much of the temperature has been rising in recent 100 years. So after the Industrial Revolution, the global temperature is keep going increased up and up. And especially looking at recent several decades, we can find very steep increase of the temperature rise. And IPCC report, which is made by the many researchers around the world, says that this sentences. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. This unequivocal means defined in the report is a 99% confidence of the increase of the temperature. And looking back the previous report by the IPCC, the percentage is much more lower. But in recent years, it is pretty much confident that we have this kind of temperature increase induced by the human activity. Next, please. And the 1.1 degrees Celsius, how do you feel this number? Is it very hot or not so much? Very hot, no? But imagine that maybe today's Chiba in Japan, temperature is like 25 or something like that. And that tomorrow we're gonna have 26, just increase 1.1 degrees Celsius. Do you think it's very hot? No, maybe. But the key point is the 1.1 degrees Celsius is the global average, not just like this place. Global average increase of the 1.1 degrees Celsius brings us very much more like severe effect of our human lives. the one of the effects is like this one, the very severe rainfall, and also we have this kind of very extreme floods induced by those rainfall. And so we have to prepare those severe climate or weather events and disaster. Please next, please. Yes. And this figures is also from the IPCC report. Left-hand side, we have the simulated change of the global temperature. This, looking at this, you can see that this simulation is based on the one of the worst scenario of the human beings are keeping using fossil fuels much more and more. And that results in maybe 4 degrees Celsius of the global warming. And looking at this distribution, you can see very uniformly the temperature is increasing. But on the other hand, this one is the result of the global warming of the 4.4 degrees Celsius. This is for the simulated change of the annual mean precipitation change relative to that decade. So very clear differences between those two. I mean, this figure has very clear separation of the dry region and the wet region when compared to that uniformly increased temperature. And that's why we are very much more careful about which region is getting very drier or wetter or something. Next, please. And we need to know those which regions getting drier or wetter, but human beings, do we have enough observation to prepare like the increased precipitation or decreased precipitation? This is one of the answers. This is the distribution of the rain gauge station around the world. Looking at this one, so maybe like in the US or the European countries, developed countries, we have very dense observation network. But if you look at the, let's say, the desert or the rainforest area, or like developing countries, very much sparsely distributed or no observation can be obtained. So, and additionally, of course, looking at the ocean, we don't have zero observation we have. So we need to observe the rainfall from the space. Next, please. And this satellite is today's main topics called Global Precipitation Measurement for Satellite. And this is the, as introduced by Brian, joint mission of the JAXA and NASA, which carries 2 main sensors. One is the GT microwave imager, GMI. This is developed by the US, NASA. And the other one is the dual frequency precipitation radar developed by Japan. And this satellite is very much specialized for observing precipitation very in detail. Let me explain more detail from following slides. Please, next. Maybe one more click. Yeah. This is the observation image of the GPM satellite. We have this kind of broad observation of the hurricane or typhoon by the GMI, which is microwave imager. This sensor can be obtained the electromagnetic wave, microwave from the precipitation particle. And this is the very key point. And looking at this movie, we have the like CT scan observation. Vertical distribution of the precipitation can be observed by the radar because radar emits the electromagnetic wave by itself and reflected by the precipitation particle can be get by the sensor. So we can see that how much distance is from the satellite to the precipitation particle. Next, please. Maybe 2 more clicks. Thank you. So various sensors are used for observing the precipitation. So one of them is as I already introduced, precipitation radar, and also the GMR-like sensor, microwave radiometer. And the other one is the infrared imager. All those have the different roles or features to observe the precipitation. As I introduced, precipitation radar actively emits pulse and measure the echoes reflected back from those. And this is very much, by using the radar, we can know the very detailed distribution of the precipitation, but we can only get this narrower white source with. And on the other hand, microwave imager, we can get this kind of very much broad white source. And this gets possibly electromagnetic waves distributed by those precipitation particles. And lastly, we have the infrared imager like Himawari, or goes by the US. This observes not directly observes the precipitation particle, but this one observes the cloud top temperature, so that we can estimate how much of the precipitation is going on under the clouds. So by combining all those different sensors, we can see how much of the precipitation is occurring in the entire globe. Next, please. One of this activity to combine or observe the global, not only just the band, but global precipitation distribution is the GSMAP. This is the dataset produced by JAXA, which stands for Global Satellite Mapping of Precipitation. And as I introduced, this product uses 3 different satellite sensors. We are using GPM DPR, which is a radar on board the GPM, as the reference standard of those other sensors. And in this map product, we are mainly use the microwave radiometer because we have a lot of this type sensors among the different countries. So JAXA gathering those data as much as possible. And using this one as a reference standard, we can combine those observations. And additionally, after combining those observations, even after combining, there is an area that we cannot cover by those observations. So we use infrared imager like Himawari type sensors to compensate of those unobserved areas. Please, next, please. So this is how we make the GSMAP product. And a quick one. Okay. Oh, maybe yes. Is not moving. So the band shows the observation area of the different satellite. As I told, just one satellite cannot cover the entire globe. We have very much unobserved area among those bands. So but we can obtain the information from the infrared imager like Himawari, this type of cloud information, and that enables us to estimate how much of the rainfall going on under the cloud. So by merging those all satellites data, we can have the global precipitation measurement. Next, please. This one. This is like just the product after product. And unique advantage of the GSMAP is clearly you can see we now have the observation over the ocean, and like that one coming to Japan, the hurricane. Before coming to the land, we can see or know how much of the precipitation coming to our land. And rainfall can be measured globally, continuous and same interval and consistent accuracy. And all those products are freely available by this kind of website. And we are now many users from 150 countries or regions as of the last year. So if you have interest, please check this website. Next, please. And GSMAP product have different versions for different users or the field. The column shows the latency classification. As we going this side, the latency is very better. But going this, the low latency. And the low shows the data used to produce GSMAP product. And the top row is only based on the multi-satellites. But the lower row shows the gauge adjusted. Not just like using the satellite-based data, but we also have the, the rain gauge station, so we can adjust for some correction to produce much more accurate precipitation map. So users can choose based on what they want to do by those precipitation datasets. Like if you need to use those products for weather monitoring, the latency is the key. So you can choose those products. But if you want to do some kind of long-term analysis, the accuracy is the most important point. So you can use those kind of products. So we are producing this type of the GSMAP product right now. Next, please. And by those efforts, the GSMAP is used different fields or users like education, public health, energy, agriculture, and so on. Next, please. And lastly, I want to emphasize the activity with the simulation model collaboration research. Like GSMAP, we have a lot of satellite-based products, but not only the satellite. By using only satellite product, we can know we cannot know everything about the Earth. And as I told, it is limited revisit frequency or the resolution, some kind of regulation there. So by combining those observations by the computer simulation, we can know the very dense data set horizontally, spatially, and temporally. So those are the very examples of the model collaboration research. So quick one, please. I want to introduce the GSMAP utilization in hydrology, which simulates the land water cycle. Next, please. So as Masato Ohki, which is the previous presenter, mentioned, that today's Earth system is one of the model collaboration research. Today's Earth, or we call PE, is a global terrestrial hydraulic simulation system that integrates satellite observation. This is developed by JAXA and the University of Tokyo. And these main goals are to produce realistic global long-term land water cycle datasets and evaluate them, or to provide risk indices for extremes or water-related disasters. As I introduced, we have a lot of satellite observation for the land or the atmosphere. And as use those observation-based dataset, atmospheric dataset or land dataset, we can now simulate the land water cycle using the land simulation model or river routing model. And as a result, we can get all those variables related to the Earth system. And one of them is like this one, river discharge or runoff. So we can use those variables for the disaster mitigation or prevention or like water management. The next, please. So I just quickly introduce these slides. We have several families of the TSRs, mainly divided into two, the global system and regional system. This is called TSRs Japan, T Japan. This is currently under operated in real time. And this is also doing the forecast, but due to the law, we only provide those data for the proprietary researchers. Therefore, global system, we are now planning to update 0.1 degree horizontal resolution. This is like 11 kilometers resolution for entire globe. And we are now going to prepare to do some forecasts for several days. So if you're interested, please refer to this website. Next, please. Yeah. Wait a second. One more. Yes, this is one of the quick results of our simulation system. As you can see, this is river. Like blood vessel. You can see the temporal changes of those river flow. And one more click, please. Looking at very regionally, this is a very coarse resolution, but this is for the higher resolution, especially made for Japan region. This is a case study for Tangibis, happened in 2019. Using that, we can simulate the flood risk beforehand. And some of the many points that our system predict there is a very high risk is pretty much reasonable, pretty much corresponding for the dike break points like this. One more click, please. One more, please. Thank you. Yes. This is river discharge, but we also got like information for the soil moisture. And looking at the soil moisture, we can see how much of that region is getting drier or severe drought situation. Maybe several years ago, Europe, maybe every year recently, several years ago, Europe experienced a severe drought. That situation is also partially simulated by the TSRS system, like drier, very much wet is spread among those countries, like this one. The next, please. Yes. And this TSRS system is utilizing the satellite observed data as much as possible, like land use by ALOS or the water body map by the optical imagers. And also, of course, we are using the GeoSmap as I introduced at the beginning. And those data was used for the simulation, and the simulation can tell how much of the flood risk is coming in like several hours later. And based on that information, we can decide where to observe, the like emergency observation by the ALOS satellite, as Ohki Masato is introduced previously. And that observation image or data can be feedback for the simulation. And also, our simulation result is used for those image processing to make more accurate or more area to provide those information for the users, like local government. The next, please. Yes, that is our overview of the activity. And just one thing, as I introduced at the very beginning of this presentation, tomorrow morning, 7:20 a.m. in Japanese Standard Time, the Alpir is going to be launched. This one is the joint mission of JAXA and ESA, European Agency, and especially JAXA and NICT developed CPL sensor. This is sensor name. for observing cloud. So many other three sensors are also on board, and by using those all sensors, we can see clouds, aerosols, radiation observation. So stay tuned for this launch. Thank you very much.
Other than like 2 questions for you because of the time. Let them ask you. All right. And when they ask the question, if you could repeat it, because could you repeat their question before you enter it? Okay. Right. Okay. With the time remaining, I'm going to take 2 questions for our speaker. Does anybody have a question for him? Okay.
So, so I know you mentioned like the sensors, like it captures like the heat, like senses heat, but like aren't like the satellites really far away from Earth? Because I was just wondering how like doing that for capturing the heat.
Thank you for the question. She just asked me about the sensors for sensors catches the heat of the maybe cloud top, as I thought. Because the sensor is very far away from the Earth's surface, and how we can know that? That's maybe that's the question. Thank you for asking. But maybe many of you already have seen like the infrared thermal camera or in the TV show or something. That is physically same as on board in the satellite, and that thermal camera relatively a higher resolution, so we can get the electromagnetic wave from the cloud top surface, and that can convert it to the brightness temperature, so we can see like that. So basically the same.
And who has one more question? I want to take one from this side of the group now. Okay, I'll come to you.
日本語で質問します。人工衛星って宇宙嵐みたいなのが起こったらどうやって対応するんですか？
ありがとうございます。まさに多分ホットトピックだと思うんですけど、今、すごく磁気嵐が強い時期だと思うんですけど、基本的にその磁気嵐が強い時期だと言って、衛星の運用、特に低軌道を回っている地球観測衛星みたいなものの運用をすごく変えるっていうことはないです。なので、それによって、例えば、大気の抵抗、すごい低いところを飛んでいると、微妙にこう、大気がまだ若干あるような宇宙空間を飛んでいるので、磁気嵐が強くなると、そこの大気の抵抗っていうのが結構強くなるんです。そうすると、だんだんこう、摩擦で衛星が落ちてきちゃうので、それをこうちゃんと元の位置に上げてあげるようなオペレーションの回数が増えるので、回数が増えるっていうことは、その燃料を噴射してする回数が増えるので、当然燃料の消費が早くなる。そうすると衛星自体の寿命が短くなってしまうっていう効果があるんですけども、その磁気嵐が来たからといって、すごくオペレーションを変えるってことはないんですけど、影響として寿命が短くなってしまうみたいなことはやっぱりあるっていう。で、それを回避するために、回避しようと思うと、例えば、そのもう磁気嵐の影響がない、大気からすごい遠いところに、要は高さを上げるみたいなことをする場合もあって、実は今日僕が紹介した GPM っていうのも、ちょうど去年、それもあってですね、寿命を延長させようということで、軌道高度を数十キロ高くしたんですね。ただそれを他の衛星も全部やればいいのかというとそうでもなくて、衛星はやっぱりいろんな役割があって、高くすると当然人間の目も一緒なんですけど、距離が離れるので、すごく解像度が悪くなっちゃうので、欲しい情報が得られなくなってくるっていう、そこのトレードオフがあるんですけども、GPM っていう今日僕が紹介した衛星に関しては、 そこのトレードオフを検討した結果、寿命を伸ばした方が絶対いいだろうということで、ちょっと上げたという、そういうオペレーションをすることはあります。He just asked about the, how can I say, the electromagnetic surges. That is very a hot topic recently. And in that situation, what can we do for the satellite observation? And I just answered, we don't do some special operation for that surges, but GPM satellite, as I introduced, just operated, just changed its altitude set to up several, then maybe 30 kilometers or something like that, to avoid the friction of the atmosphere induced by the electromagnetic waves, electromagnetic surges. And that kind of avoidance can be considered. But as a result of those operations, we lose some horizontal, I can say, resolution or the sensitivity. So it's kind of trade-off. So sometimes those kind of trade-off happens, and we are considering those trade-off to decide the operation.
All right, so the last part of this webinar, I'm going to now pass it over to Peder Nelson. And once again, he is coming to you live from Oregon State University. Right now, I believe it is 12:30 in the morning there, and he'll be talking to you for about 10 minutes for the end of the webinar, but he's going to bring some things together and mention some of the things that he has been working on and that align to what you've just heard from the last two JAXA speakers. So Peder, let me pass it to you.
Well, thank you very much, Brian. And I am really excited to end our webinar here, because we've heard wonderful science and about all these data products that are coming out. And what we want to do is invite you to be part of this science. And I think that's a really important part of what we're doing, is that there's many, many people involved. And you've heard from two scientists that are doing wonderful work and providing us a lot of data. And so one of the things that we focus on here is using a mobile app called Globe Observer. And this right here is one way that you can actually do remote sensing. Like somebody asked earlier, we're taking photos, optical photos of the way that the sunlight reflects off of surfaces, right? And that can tell us things about water. It can tell us something about vegetation. It can tell us a lot about the surface of the Earth. And so it's amazing how using this tool can help provide some evidence to these scientists that are trying to make sure that they're mapping the world right. And that was a lot of what we heard earlier, was how do we know that what we're mapping is right? Are we getting it? Are we getting the water where we think that water is actually falling out of the sky? So one of the wonderful things that you end up doing when you take these photos, one, you submit it to a database. And this is a database that NASA helps to run for the 127 globe countries. And here on this map, you're seeing places where people have submitted ground photos, like what you're seeing here, remote sensing images. And, in this location, we can actually see some very tall trees in our up photo. And when we look around us in each of our cardinal directions, to the north, to the east, to the south, and to the west, we can see the types of trees that are there. We can see if they're healthy or not. We can see how green the vegetation is. And all of that relates back to when or where water falls, right? And so one of our big questions for scientists and everybody on Earth is, when do we actually get leaves on trees? And so you can see over the last 5 years, we've been able to identify when trees are losing their leaves, and also see where leaves start coming out at different times of the year. And so this is the type of data that students all around the world are putting together, and are things that you can use as part of your own science. And we were just talking a little bit about water and flooding. And one of the questions that we have when you take your photos is, do you see standing water? And this is one of those questions that scientists are trying to figure out. Is that water up in the sky, or is that water on the ground? And you can see that we have some differences. Now, are they meaningful? That's some of the questions that students are investigating and are trying to figure out. But this is available to all of us using the Globe Observer mobile app as a way of collecting data together like this. Now, one of the things that we're always curious about is where are the trees in different places around the world? I was really pleasantly surprised to find out that, at least according to these satellite-based maps, Japan is almost 80% forest covered, which means that we should be getting a lot of participation, a lot of photos, and helping us to understand what is the height of those trees, and when do they have the leaves on their branches. And so what's really wonderful about satellites in space is they can be consistent and take pictures over 4 or 5 years. And this is what allows us to look at changes in an area. And here, what's really interesting to see is we're actually seeing a little loss of tree cover and a small increase down here of built up urban areas, just a very small amount. And so scientists have made a prediction about where they think that's happening. And this is where you can get involved and see, are those scientists describing your area correct? And I want to end with my invitation here with something brand new that just came out. Now, many of you know about Facebook and the company Meta. Well, one thing that they have done is help to analyze satellite imagery, and they have made a map of tree height at 1 meter resolution on the ground. This is brand new, and all of us scientists are looking at this and trying to figure out, did they actually map out the trees right in your area? And so if you zoom in, you can start to see the detail of what was mapped, and it really is astounding. And so one of the things that satellite imagery gives us is data, but it's not always right. And this is where you can actually get your research career started and work with us to look at some of this data that has been presented to you today. And that's where the research is possible, where you can be part of the science, because we can measure a lot of things from space, but what do they actually look like on the ground? And are we getting those maps right? So I hope that what you've learned today is exciting and invites you into ways that you can actually use satellite data in your own work to understand the world around you. I hope that you have a great time with the rest of your conference, and we'll be rebroadcasting this for the rest of the globe countries that are currently asleep.
Let me know when I'm good. All right, thank you, Peter. So if anybody asks a question, do I hold the hand out? All right, so we have time for 2 questions for Peter, if you have any, and then we will need to finish the webinar for today because we have several Hyperwall talks coming here after this from JAXA and NASA. So does anybody have any questions for Peter about any of the data information that he mentioned? All right.
Yeah. Hi, and my question is, why are tree heights so important?
Yeah, tree heights are really important because trees tell us whether there has been disturbances like wind. If you have a lot of really short trees, that usually tells you something about the environment. And where I live in the United States, our trees are some of the tallest around in the whole entire world. And that's because we don't have a lot of forest fires or a lot of floods or a lot of disturbance events. And so some of our trees where I live are over 1,000 years old. And that is a place where carbon gets stored, where animals make their houses themselves. And so it's a great way for us to understand the health of an ecosystem, because trees are usually the last thing to emerge after you have grasses or shrubs, and they're only there because they can make use of all of those resources over a long period of time. And so it's just amazing what you can find out by just looking and understanding the height of that tree and where that tree is located. Great question.
All right, thank you, Peter. Okay, one more question for the webinar. Okay, Sam went up first. Let me pass it over to him.
In like the first website you showed us, there was like a giant decrease in like green tree coverage, I think, in like 2019. And I don't think anything that big happened that year. It's like, so there's probably like something like there's a lot of like things that happen to the data. Is there any way to like get rid of the inaccuracies? Since like I think since it's mostly done by like people that might not be experts or people that like fully on like professional scientists, is there like a clear-cut way to get rid of all of the inaccuracies?
Yeah, and yes, that's a great question, because that is the science that happens here. This database is all the contributions that come in, and one of the first things that scientists or anybody who uses data wants to do is make sure that you're working with good data, right? So you do need to go in and look at where these observations were made, maybe who made them. Is there any overrepresentation of a certain area and maybe no measurements coming from another area, similar to the rain gauge issue that we saw earlier? And that is part of what you actually see in this data. When we look at who participates, we actually see the Northern Hemisphere is mostly where we're getting our observations. And that also corresponds really well with what we see in the months of November, December, and January in the Northern Hemisphere. So part of what you see whenever you are looking at data, it can actually be an observational bias. So when anybody presents maps or graphs to you, think critically in exactly that way that you mentioned here. Why might this have occurred? And is it actually that phenomenon happening? Or could it be the instruments that we're using might be leading us astray or might need to be improved in some way? And that's where you guys will be able to make your careers, is actually picking apart and really being questioning of data that's presented to you. And don't just accept that because somebody who has gone through a lot of education or training is giving you at all the correct results. So I really appreciate this critical thinking, because that's what we want you to do in this campaign, and get involved with this raw data like this. Figure out, why do we have some of these weird trends like this? And that's your contribution to science. And that's how we can all improve on our data or our understanding of the world around us. So I know with that, thanks so much for your time, and good luck with the rest of your presentations there on the Hyperwall today.
Yeah, thank you so much for that question, because that's something that we've been talking about a lot in the campaign, that do we trust the data all the time? And it's a great duty for you to look at that data and make sure that that data is correct. So can we give Peder Nelson a round of applause for his presentation? All right, and thank you all for being here. This is great. You've been a great crowd. We have to end now, like I said, because we have some NASA JAXA Hyperwall talks coming up as part of the Japan Geoscience Union meeting happening right now. So I'm going to adjourn the webinar. And once again, thank you all for being here.